Alrighty, cool. Well, so welcome again. My name's Justin Labar. I'm from Google, and I work on CUDA compilers. So that's what we're going to talk about today. I have a thesis for this talk. CUDA is a low-level language. And to prove this to you, what I want to do is show you some CUDA code and kind of argue that if you want to write at least this particular algorithm, but probably a lot of algorithms that you care about, on a GPU, you're going to want to write them in a low-level language. And CUDA is a low-level language. But before I can actually show you this programming language and argue this, I need to actually sort of explain to you what GPU hardware looks like. The issue is I can't show you the code until you understand what the hardware looks like because CUDA is a low-level language. So that's kind of going to be the framework for the talk. First, we're going to build up a model for what a GPU looks like. Then we're going to write some code, and we'll think about that. And then finally, we'll talk about why I'm excited that open source Clang can compile CUDA code today. You can go download TIP and build it yourself and compile it and ignore the rest of this talk if you want to do that. Okay, so let's get started. I have a couple caveats about this model that we're going to build for a GPU. Caveat number one is that I'm a software guy, and so this is just going to be a model for how the hardware works. And number two, in this model, I'm going to be using kind of different terminology than NVIDIA uses for describing their GPUs. So be aware. All right, so this, I hope you guys can see this, awesome, is a modern CPU. This is a Haswell CPU. This is from 2014, 22 nanometers, and 18 cores. And I claim that this CPU has some design tensions. The CPU is trying to do two different things well. Number one, the CPU is trying to do the following thing well. I have one core with, say, one thread running on it. And what I want to get is the fastest performance from that one thread. I want to get through that thread's business, whatever it is, as quickly as possible. Number two, what this chip is trying to do well is I have maybe 36 threads running, 2 threads running on each core because I have hyperthreading. And I'm doing stuff on all of them. And I don't care how quickly any one thread finishes, but I care about how quickly this whole set of threads completes their task, whatever it is. And I claim that there's actually an inherent tension between these two goals. And one way that you can see that is that when I fully load the CPU and I'm running all 18 cores at 100%, it actually decreases the clock speed so that this chip doesn't melt. But if I only am running one core and maybe one thread, it increases the clock speed so that that one thread runs more quickly. Right? So even on the CPU, we have this design tension, and we have things to kind of trade off between these two things. What we're going to imagine doing is transforming this CPU into a modern GPU. And the main difference, like in philosophy, is that on the GPU, we don't have this design tension. We're only designing for one of these two things, and we're designing for the second thing, which is I have a highly data parallel program. I'm going to spawn a gazillion threads, and I don't care how long any one of those threads takes to complete. All I care about is how long does it take for my whole program, which we're going to call a kernel, but this whole data processing step to complete for all of the threads to complete. Okay? And the assumption is we're just going to have a bazillion threads running at any given time. So the way that we're going to go about kind of designing our GPU, and again, this is just like the software guy's model for how the hardware actually works, is we want to shove kind of as much compute as possible into a given space of silicon. So we're going to take our 650 square millimeters of this chip and try and put a lot more compute on it. So the first thing that I noticed, being again, a software guy looking at this thing, looking at this die shot, is all of the area spent on cache. So that's this area here. This chip has some absurd amount of cache. I think it's 45 megs of last level cache. So on our GPU, the first thing I'm going to do is just substantially reduce this. We're going to go from roughly 50 megs to roughly 5 megs, or maybe 45 to 4 or something like that. Now, it's up to me to kind of justify to you that this is a good thing, but notice that it definitely gets us more compute, just because I can put more cores on here. I could put roughly 50% more cores on this chip just by reducing the cache significantly. Now, obviously, I get 50% more cores, but I don't necessarily get 50% more performance. So it's up to me to kind of explain the things that we do on this chip to kind of improve the performance beyond that. But that's going to be our first optimization. We get rid of a lot of the cache. So now, kind of, I need to focus on the cores themselves. And again, we're going to just kind of modify these cores until they look less like CPU cores and more like GPU cores. So again, it's just kind of a study in contrasts. Let me make sure this is on page. On a CPU, the first thing that my overall goal is going to be to simplify the design of the cores so that they get smaller and I can just put more of them on the chip. Okay, so the first piece of complexity that I notice on a CPU when I'm thinking about this is that a CPU has both scalar and vector instructions. So like a modern CPU from Intel, you can do add EAX, or you have some vector instruction operating on vector registers, right? So the CPU ISA has scalar and vector instructions. But on a GPU, our assumption is that we're doing highly data parallel computations, and that's all we care about. So I can actually simplify this greatly. On my GPU, my ISA is only going to have vector instructions. And I should say this applies to the NVIDIA GPUs I learned today. It doesn't apply entirely to AMD GPUs, but CUDA runs on NVIDIA GPUs, so that's kind of what I'm focusing on. Okay, so already we've kind of halved the size of our instruction set. That was easy. All right, great. So I want to think a little bit more about the instruction set. When I think about especially a legacy desktop CPU like an x86 CPU, it's less, I think of it as a CPU and more like an x86 compiler. I give it x86 assembly, and then it really understands this assembly at a deep level. It translates the assembly into microcode, and then it optimizes the microcode. It understands, for example, that if I say XOR EAX, that I'm zeroing out the register. And there's hardware in there to understand that and to not actually do the XOR and to, that affects our register file and all kinds of complicated stuff. But the price of that is that I have really complicated decode logic on my CPU. So here I've got this backwards compatible ISA. So that I can run code that was compiled in 1980 on a chip that was made in 2016. And it's complicated. And I'm obviously constantly adding new instructions to my ISA, and I basically have to support them forever. So that's a kind of a cost that we pay on the die forever with the CPU, and it kind of keeps increasing. So wouldn't it be nice if I could design a chip where every time I make a new architecture, I change the ISA. I completely change the instructions. That's actually what we do on the GPU. We have a non-forwards, forwards, and backwards compatible. Each time we come up with a new GPU, we change the instruction set architecture of the GPU. But there's an obvious problem with this, right? Which is that if I'm in the business of selling GPUs, and I go to you and say, I have this awesome new GPU, but in order to actually run anything on it, you have to recompile all of your code. You might be less inclined to give me some of your money in exchange for this GPU that I've just manufactured. So we'd like to solve this problem while still reaping the advantages of having a non-forwards and non-backwards compatible ISA in our GPU. So the way that we do this is by using literally the only trick that we have in the book as software developers, and that's to introduce a new level of indirection. So let me show you how that works. So we write, as a software developer writing for the GPU, we write CUDA code. And I'll show you some CUDA code later in this talk, but it's an extension on top of C++. And then you take this CUDA code, and you run it through a compiler. You can run it through NVIDIA's compiler, NVCC, or now you can also run it through Clang if you want. These compilers don't emit machine code. Instead, they emit this high-level assembly code called PTX. And this stands for Parallel Thread Execution. I say PTX is a high-level assembly code because it's missing a lot of the things that the machine code actually needs. For example, PTX has unlimited registers, virtual registers, and the register allocation is saved kind of for later in the process. Similarly, PTX is actually missing some instructions that the hardware needs in order to actually run your program. So great, so we have this PTX, and this is the forwards and backwards compatible ISA that we target. There's a book describing what PTX does. And you could even write this by hand if you wanted to. Then we take the PTX and we run it through PTX AS. This is NVIDIA's closed source optimizing assembler. And it translates the high-level assembly into machine code. The machine code is called SAS. I haven't found a canonical description of what this stands for, but the best guess I found on the internet is shader assembly. I don't know. And PTX-AS can compile to SAS for all of the different architectures that it knows about. Right. So when I buy a new chip, I just have to upgrade my PTX-AS, and then I can recompile my existing PTX to SAS for the new chip. Then when we actually package up our program, here's how this works. Clang and NVCC will take all of this, the PTX and the SAS, and package it into the host binary. And when you go to run the program, it will look and see, do you have any SAS for this binary, for this GPU that you have in your machine? If so, I'll run that. If not, I'll take the PTX and actually compile it on the fly using the GPU driver. And it's, the GPU driver's got a copy of this guy in. Okay. So this is good from a compiler developer's point of view, because it means that every time NVIDIA releases a new GPU architecture, we don't have to write a new backend in LLVM or Clang. But it's also kind of bad from a compiler developer's point of view, because PTX-AS is an optimizing assembler, and it will do things like loop unrolling. And I, as the compiler developer, probably would prefer to be in full control of whether my loops get enrolled, and if they do get enrolled, how much they get enrolled. Similarly, when I'm writing Clang and I'm emitting PTX, I have no idea what the final register allocation is going to be. And knowing that would probably influence, for example, how I might inline functions. But I have only very crude control over the decisions that PTX-AS makes. So I can say don't unroll this loop, or I can say things like don't inline this function, but that's kind of all I've got. So that's the trade-off, but we don't have a ton of choice. Some people have tried to reverse engineer SAS, but that's not what we do in Clang, and that's not what NVCC does either. We just submit the PTX and we live with this trade-off that was made kind of for us. Okay? So that's how we get away with changing the ISA on each new architecture, and that is, again, a simplification to our GPU core. Cool. So then, a CPU, a modern CPU, does all kinds of crazy stuff to improve the single-threaded performance of your code. So, some keywords that you might know is the CPU does out-of-order execution, it does register renaming, it does really complicated branch prediction. It does really complicated prefetching, because we really want our data to be there when we use it. If the data isn't there, it's going to be very expensive for us because our core is just sitting around doing nothing. And the CPU is highly superscalar, meaning the CPU tries to do many different things all at the same time. I think these new Skylake CPUs have 7 ports on them, so they can do 7 different things with some constraints at a time. And these are all important optimizations for a CPU to get maximum single-threaded performance on them, but they also cause a lot of complexity on our die, and so they make our cores bigger. And again, we want to shove as much compute as possible onto our GPU. None of these things are execution units, right? So we take all of them and we either get rid of them or simplify them. So the GPUs, the modern GPUs that I'm looking at, they have some limited out-of-order execution, but it's nothing like a CPU. It's just you give me 2 instructions, I will try and execute them at the same time if they are not dependent on each other. They don't do any register renaming as far as I know. They have simpler branch prediction, simpler prefetching, actually probably no prefetching at all. And although they're superscalar, again, it's to a much more limited degree than a CPU. So let's just say all simpler. All right, and again, this just lets us make our cores smaller and put more of them onto the die. So far, we've designed a GPU that has a lot more cores than a CPU. The top-of-the-line GP100 GPU from NVIDIA has got 60 cores on it in the same area as that Haswell chip that we were looking at that has 18 cores on it. But on the other hand, this quote-unquote CPU or GPU, whatever, hybrid thing that we've developed also sucks. And the reason it sucks is because all of these optimizations here, the cache and out-of-order execution and so on, they were there for a reason. And by getting rid of them, not only did we hurt our single-threaded performance, which we don't care about, but we got 3 times more cores, but we hurt a lot more 3x in performance. So so far we haven't won anything. We've just designed kind of a bad CPU. So we need to do something different. And this is where kind of the one piece of additional design complexity in the GPUs comes in. On a CPU, you probably, I want to make sure I'm on, all right. On a CPU, you probably have hyperthreading. If you have an Intel CPU, it means you can run 2 threads at the same time on a core. If you have like a power CPU, I understand they go up to 8 with some like limited performance, right? And these two threads that are running on the core share resources. And it means that if one thread is blocked waiting on memory or whatever, the other thread can still run. On a GPU, we also have hyperthreading. But we have hyperthreading up to 64 threads per core. And what this means is that I don't feel the pain from losing a lot of these optimizations or from losing the cache in particular. Because if I have one thread that is blocked on memory, and like it's probably likely to be blocked often when it goes to memory because I have much less cache on my GPU, that's fine because I have 63 other threads running. I can just pick one of them. And hopefully some of them have like arithmetic to do, and I can run that arithmetic. So this is the major like addition to complexity on the GPUs. But we only get to do this, this is only sensible, because we have this assumption that we have a gazillion threads all running in parallel on the GPU. And again, like that's not our assumption when we're designing a CPU. So the fact that I wrote less than or equal to here should worry you a little bit. So I want to dig into that. This is kind of the first place where we as software engineers need to be kind of pretty aware of the hardware architecture. So on a CPU, you have some number of registers in the ISA. So like on x86 64, you have 16 registers available to you. But I claim that these registers, like as you use them, they're just kind of the working set, quote unquote, registers. By which I mean, if you have some like whole program and you need 17 registers, like that's not a big deal. You just push one register onto the stack. And when you need it again, you pop it off the stack. And that's cheap because your stack lives in L1 memory. And like maybe it gets pushed down to L2 memory or something, right? But like you're not going to main memory to service your stack. But on a GPU, remember, I substantially reduce the size of the caches, and I also substantially increase the number of threads that are running at any one time. So the amount of cache available per thread is much smaller. And that means that if I choose to go to the stack, I can do it, it's going to work, but I'm probably going to memory every time I push and pop. And that's going to be pretty expensive. So on the CPU, like we're happy with our quote unquote 16 registers because we can just push and pop on the stack and that's not a big deal. On the GPU, we're much more concerned about going to the stack. So we have a trade-off that's presented to us by the hardware. If we have some program that needs in total more than 32 registers, so this happens, let's say it's equal at 32 registers per core, or I guess I should say per thread. If I have some program that needs less than or equal to 32 registers, then I can fit 64 threads on the core. If I need more registers than that, I could go to the stack, and that's one option, that's fine. Alternatively, I can use more registers, and the hardware is happy to let me do that. But the downside is I get fewer threads per core. So this means that as a programmer, like you need to be aware of this, because writing kind of simpler, smaller programs with more threads is probably going to be more efficient on the GPU than writing more complicated programs with fewer threads. Because the simpler programs get higher occupancy, we can then better hide the latency of expensive operations on the GPU. So this is kind of the first way that writing for GPUs is like inherently, I would say, a low-level proposition if you care about getting performance. All right. So that's all I want to talk about. Well, so to conclude kind of this thing about the GPUs, the kind of nuts and bolts of it is that if you look at the biggest and baddest Intel CPU I could find is this equivalent of this Haswell chip, but the newer architecture, the Broadwell chip, 18 cores. If you just sit spinning doing fuse multiply adds like the whole time, you get like 900 gigaflops per second. This GP100 GPU that NVIDIA has just come out with, the equivalent number is 10 teraflops per second. And that's on a die that's the same size. So that's how we're able to kind of fit in roughly 10x compute on the same amount of die. But like, as you can see, there are trade-offs, and it only sort of works for certain kinds of applications. All right. So now I want to start to sort of segue into thinking about how we write code for this. One of the sort of weird things about writing code for the GPU is that the assumption is you've got a gazillion threads all running at the same time. We need to impose some kind of organization onto these threads. Otherwise, it's going to be kind of mind-blowing to get them to do anything coherent. So the sort of hardware and programming language cooperate to impose structure upon the threads. And I need to explain that to you before I can actually show you any code. So actually, like, before I even explain this to you, I need to unfortunately change a little bit of the terminology that I've been using. So far, I've been talking about threads as the things that run on the CPU. And we're going to rename these hardware threads. So these are threads that are always running in a SIMD fashion. At every clock cycle, they do 32 things at a time, because that's the width of our SIMD unit on the GPU. It's 32. But when we actually write code, the terminology that NVIDIA uses, and that I think sort of makes sense, or at least is hard to change in a presentation, is that the individual, what we call a thread, is actually a single lane in the SIMD unit. So to be concrete about this, like when I write int x equals 5 in my CUDA code, we say that like this is a single thread running int x equals 5. What's actually happening is there's some SIMD register with 32 elements, and I'm putting 5 in each of them. Yeah. So we're going to call this thing that is like the unit of execution that like is running the code that we've written a quote-unquote software thread, or maybe just a thread. And we're going to call the thing that like is actually happening at the hardware a quote-unquote hardware thread, or in NVIDIA's terminology, they call it a warp. This name comes from weaving, which was the original parallel threaded technology. Okay, so how do we like organize these threads and the warps and so on into something coherent to actually do something useful? So we have up here at the top of the hierarchy threads. And we said we have 32 threads and a warp. Again, this thing we can think software thread, this thing we can think hardware thread. We organize the warps into what we call blocks. A block is a group of warps that always runs on the same core. There can be, in the ISA, it just specifies it's up to 32 warps in a block. And then we organize the blocks into what we call the grid. The grid, is the full set of all the threads that are cooperating to do whatever computation we're interested in on the GPU. We can think of that as sort of like the whole program. And there can be a lot of blocks in the grid. It's something like 2 to the 20. It sort of depends on the shape of the grid. And we'll talk about that a little bit. But for our purposes, we're just going to say this is infinity. Okay. So each thread knows its position in its block and in its grid. So what do I mean by that? When you launch the kernel, when you launch your program on the GPU, you specify first the block dimensions, which is 3 dimensions, but I'm just going to draw 2. So this is block size dot x, and this is bs dot y. And there's a bs dot z too. Yeah. And a thread knows its position inside of the block in terms of x, y, and z. And then similarly, when I launch the kernel, I also tell it how many blocks, and I tell it the shape of the grid. And a thread can also query this number, which is the block index.xyz. So each thread has associated with it 6 indices. And the shape of these two things is specified by me on the CPU when I start running code on the GPU. Okay. And we can query these things from the thread. And so the thread uses this to kind of figure out what data am I supposed to be processing at this moment. Okay, cool. So I think with this, we can actually start writing some code. So let's do that. So the algorithm I want to show you today is what we call a full reduction kernel. And so what this is we're going to take just a list of integers and we're going to add them all up. And normally, if you were writing this code in, say, Eigen or Thrust or any of these other kind of libraries, you would probably write this as a templated function, and so it wouldn't be a list of integers, it would be a list of t's, and you would also template on the reduction function. So instead of just doing addition, you would be able to do addition or multiplication or take the min or take the max or something like that. But we're just going to kind of simplify it and do addition. So the way I'm going to structure this algorithm is first, each thread is going to add up 4 elements from the array. So it's going to kind of figure out which 4 elements it's responsible for, load them all into memory, and then add them up. And then within the warp, remember that's the hardware thread, we're going to do what we would call in SIMD land a horizontal add. We're going to add up all the values that we've accumulated in the warp. And then we're going to do the same thing in the block. Remember, the block is the set of warps that are all running on the same GPU core. And then finally, we're going to do that kind of across the grid, across all the threads that we're running on the GPU. So we'll get to see all layers of this thread hierarchy in this code. Okay, cool. So let's write this. We use the __ global attribute to say that the function we're about to write is a kernel function. And the kernel functions are functions that we can invoke from the CPU to start a computation on the GPU. Kernel functions always return void. And we'll call this full reduce. And now the arguments it takes are pretty simple. We have a pointer of ints. We have a size tn. And we have a int star out. Cool. All right, so first thing we have to do is declare our sum equals 0. And remember that in the hardware, sum is actually a vector register of width 32, and I've just initialized all of them to 0. And now I also need to figure out, like, where do I start? Okay, so to figure out, like, which elements this particular thread is interested in using, needs to add up together, I need to consult the thread index and block index, and that's, remember those kind of interlocking squares that I drew. So I'll write this and then we can kind of think about what it means. Okay, so this 4 comes from the fact that each thread is processing 4 elements. And then basically, I'm ignoring thread index.y and z and block index.y and z, because when I launch this kernel, I will always set the size, the dimensions of the block and the dimensions of the grid to be 1 in the y and z elements. So I'm envisioning my input as a single dimensional array, so I'm also going to set these guys to be a single dimensional array. And if you think about it a little bit, this kind of figures out where I start inside of this single dimensional array, this expression. Okay, so now it's pretty simple. We just write a loop. So start plus 4, but we also have to make sure that we're still in range. I is less than n, I plus plus. Okay, so now I could just do something like this, plus equals in sub I. And again, I should point out that this is what we would call in SIMD world a gather load, meaning I have some base pointer in, and then I, remember, is a vector of 32 indices that are all different. And I'm loading 32 different addresses into this temporary array that I'm then going to add to sum. The GPU hardware has support for recognizing if I'm doing a consecutive load of 32 consecutive addresses. It also has support for noticing if I'm doing a strided load. In this case, I'm doing a nice strided load of 4 ints. And it will make those fast. It is like perfectly happy to run your code if like the 32 different values for I are 32 random addresses. That will work, but it will be slower than if they're nice and strided. So as the programmer, if I want to get good speed out of my program, like I need to be aware of that rule, and kind of I want to make sure that this is either consecutive or strided. Okay, so I could write it like this, and that would be fine. But probably a better way to write it would be as follows. So here we're using the LDG intrinsic. LDG stands for load global, but probably a better name would be load invariant or load read only. So load, this is a special load operation that we can use on the GPU that works only if the memory that we're loading never changes during the lifetime of the kernel. So we're not writing to in, so we can use LDG. And LDG is often faster, never, in my experience, slower than a regular load. As the compiler, we would like to replace regular loads with LDGs, and in some cases we can, but you notice that it's difficult for us as the compiler writer to change this first load into the second thing, because in order to do that, I would have to prove that in and out don't alias, because I am going to write to out. So if you mark in with _restrict, then we will, in this case, replace it with LDG. But it's kind of ugly, and there are a lot of cases that we can't do this in. So this is kind of an unfortunate thing. We're sort of working on it, but for the moment, this is what you got. All right. So now at this point, I have 32 quote-unquote threads, 32 software threads, with 32 sums of 4 elements from the input. And now, again, we want to do kind of a horizontal add across all of these guys. So let me show you one way to do this. I'll write the code, and then I'll explain what it does. We're going to use another intrinsic, this time shuffle down. Okay, so what the heck does this do? I could also write this as a loop, but I think it's clearer to write it unrolled. The shuffle down intrinsic is, you can think of it as a shift of one of these SIMD registers. So again, sum is implicitly this register of 32 different values. Here's index 16 in sum. When I do shuffle down sum 16, I take this guy and I move the top half to the bottom half, and then the top half just becomes undefined. And then I add that to the existing sum. So after I do this first line, the first 16 threads in the warp each have the sums from 2 threads. And then the remaining 16 threads in the warp all just have garbage for their sum. And then I repeat this 4 more times. And at the end, I have a vector where element 0 of the vector has the sum from everything in the warp. And every other element of the vector is just undefined. Okay. So this is kind of an efficient way to do to transfer data between threads inside of the warp. All right, cool. And like, if I wrote this as a loop, I could make use of the warp size. I think it's a macro even, but I could make use of this thing and sort of like unroll it, and then I would be kind of like more agnostic to the 32 thing. But believe you me, when you see a lot of CUDA code, like a lot of it just kind of assumes that the warp size is 32 threads. All right. Okay, cool. So now let's continue. We have this sum from all the warp, and now we need to kind of combine all the different warps in our block into a single sum. So I'll show you one way to do it. There are a couple of different ways we could do this. We're going to do this using what's called shared memory. And shared memory is memory that lives inside of the GPU core itself, and it can be accessed by threads inside of the same block. Accessing shared memory is a lot cheaper than going to global memory, which is the RAM that lives on the GPU itself. I can't initialize the shared memory. I can't say shared sum equals 0. That's not allowed by the language. So the first thing I have to do is put 0 into this thing. So here's one way I could do that. Oh, by the way, this thing is not a vector. This is just one int. Okay, if I didn't have shared, it would be a vector, but because I have shared, it's just one int living somewhere in memory. Okay, so now every thread is going to write 0 into this thing, and then I'm going to call another intrinsic. Sync threads is a barrier. It waits until all warps inside of this block reach this location. There's no synchronization intrinsic that says wait until all warps in the grid reach this location. We can only synchronize within the block, within that set of threads that's running on one GPU core. There's a practical reason for this, which is that the assumption is I've launched a gazillion threads. I cannot have them all running at the same time. I have to wait until some of these threads have completed before I can start running the rest of them. So asking me to sync across everything globally would just not be feasible. That instruction doesn't exist. If I want to do it, the only way I've seen people successfully do it is they launch 2 kernels, and those 2 kernels will run in series. Okay, great. So now, at this point, shared sum is equal to 0. I could have just like had some if statement here that checked my thread index and only had one thread run into shared sum. You would have to benchmark it and see if it matters. In my experience, it doesn't really matter. All right, so we now have a 0 shared sum, and now we need to write into it. Cool, so what we do is we check if our thread index, we want to check if we are warp 0, because remember, it's only warp 0 that has a valid value for the sum. Everybody else is undefined. So to check whether we're warp 0, we do that. And now, what I want to write here is shared sum plus equals sum. But I can't do that. That would be a race condition, because I have multiple threads all accessing this variable at once. So instead, I have to do an atomic operation. I think it takes a pointer. Cool. So now we're good. And then we sync again. So at this point, after we sync, shared sum contains the sum from the whole block, from all the threads that are running on the one GPU core. So when you see this if statement, maybe like it annoys you a little bit. It annoys me a little bit. And the reason is because this whole time I've been saying that like every time we execute an instruction, it's actually at the hardware executing in a SIMD fashion. But here, only one of the threads is doing this. Only one of the threads in the warp is doing this, and every other thread is doing what? I don't know. So how does this work? When this works basically with combination with the cooperation of the hardware and the compiler, and in particular with the PTX assembler compiler, that thing that takes our high-level assembly and converts it into the machine code for the GPU. So at a high level, the way that this works is that the NVIDIA GPU, and I learned today that the AMD GPUs do this more explicitly, but the NVIDIA GPU implicitly, when it encounters a conditional branch, there's hardware support to do the following. If all the threads in that warp take the same direction on the conditional branch, we just go there, wherever that is. But in this case, that's not true. One of the threads in the warp is going in here, and the other threads in the warp are going down here, right? So in this case, we have what we call a divergent branch. And what the hardware does at this point is it pushes a mask onto a stack that the hardware itself maintains. And this mask says, only thread 0 in the warp is currently active. And then it actually runs the code inside of here. And then it keeps running until it encounters an instruction inserted by the PTX assembler that says, okay, you've sort of reached the end of this scope, whatever it is, go back, invert the mask, and then do whatever that other set of threads was going to do. So then it will go back, invert the mask, and then it will say, aha, I don't take this if branch, I just kind of go down. And then it keeps running until it encounters an instruction inserted by the PTX assembler that says, okay, now we've reconverged. And then it kind of pops off from that stack and goes back to whatever it used to be. So cooperation between the PTX assembler and the hardware, but as the compiler writers, we have nothing to do with this. So you notice that like the way I described it, it would be perfectly legal, like if I had two if statements, if A, and then I have if B. It would be perfectly legal for the PTX assembler not to reconverge until after if B. And that would mean that sort of I have maybe 4x as many, or I guess twice as many divergent states here, because I'll go in here, and then all the threads that go into if A, I keep running them, and then I check if how many of them go into if B, and then I have to pop off, and then so I have twice as much stuff that I would have to do if, in contrast to reconverging here and then reconverging here. I don't have to reconverge here. That's up to PTX assembler, whether or not it wants to do that. There is one place where I do have to reconverge, though, and that's when I run async threads. Because it would be really, really bad if we come in here, and then we activate only thread 0, and then we go in here. Then we run sync threads, and thread 0 is still the only one that's active. We wait for everybody else to get here. And then we keep running with only thread 0 active. That's not, it's not going to end well for us. The PTX assembler is responsible, therefore, for understanding the control flow of our programs, and for understanding where we have instructions that force reconvergence. And we've actually seen bugs where, like, if we write sufficiently convoluted control flow, we can confuse the PTX assembler, and it will not reconverge right here, and then you will just have bugs that cause you to tear your hair out for a month. Take it from me. That's just kind of what we deal with right now as GPU programmers. Okay. By the way, I should mention, I think I forgot to mention this, that like the machine code, the SAS code, is a closed source ISA. So like if you want to compile to it, you have to reverse engineer it to it. So like the best that we're doing is sort of like reading the output from the tools that NVIDIA has given us to kind of like sort of understand what's happening on the GPU, but it's challenging. Okay, cool. So, all right, to recap, at this point, shared sum is the sum from everything inside of the block, and now we just have one last thing we have to do, which is add into out, and that's pretty easy. So we just say, we can now pick any thread inside of the block, but I'll just pick thread 0 inside of the block. And we just do an atomic add into out. And that's it. We're done. So the reason I picked this example is because kind of at every step along the way, we are constantly thinking about what the hardware is doing and what the shape of the hardware is. And I claim that in pretty much every high-performance CUDA thing that I've ever seen looks very similar to this, is very specific to the shape of the hardware. And even if this were running on like an AMD GPU, which is in many ways very similar, it's not going to work because the warp size is different. And like the shared memory semantics are slightly different, and so on. But on the other hand, I claim that if you just spent $1 gazillion on a bunch of GPUs, you probably want to write in a language like this. And the reason is that like nobody says, I just spent $1 gazillion on GPUs, I now don't care about performance. The whole reason you bought these GPUs was to get them to run fast, and like I claim that you either need an incredibly smart compiler of the likes that I've never seen, or you need a programming language like this in order to eke out all of the performance from your GPU. And similarly, like this code is not going to run on like a DSP or an FPGA, right? That's like a silly thing to suggest. I don't think this is so bad. And the reason I don't think it's so bad is that the code that you're running on the GPU by its nature is hot code. And you don't have a lot of hot code in your program. So asking me to re-implement my hot code for a different architecture is probably not the end of the world. That's my claim anyway. All right, so now I want to switch gears and talk about compiling for CUDA in Clang and LLVM. So why am I excited that we can now compile CUDA code in Clang and LLVM? I kind of have two reasons for this. Number one is sort of related to the front end, to the language itself. And number two is related to the back end, to the optimizations you can get out of LLVM. So from the front end, and like let me preface this by saying like I'm not here to throw rotten vegetables on NVCC. Like it's a good compiler, but we're also happy about our compiler. So, all right, so let's on the front end. Like what you get from Clang is you get an actual bulletproof C++ compiler. What this means is that you get things like variadic template support. You get things like C++ 14 support, proper context burst support. All of that stuff just works today. Just download it from tip, compile with it. You also get things like, oh, and I should say that like this matters to you because not just because like you're like, well, that's fine. I just won't write my CUDA code using C++ 14, and then it will just be fine with NVCC. I don't really care. But the problem is that the way CUDA is sort of designed, you combine your host code, your CPU code, and your device code often in the same files, or at least you include some of your host headers in the file that has your GPU code. So that means that like selectively, at least some of the headers from your code have to be compatible with this compiler that doesn't support all the C++ features that you know and love, okay? Unless you're using Clang, and then it just works. So similarly, like I would say that like you get other advantages from Clang, like we're known for having fast compilation. Clang compiles CUDA code about twice as fast as NVCC. We're also known for having good error messages. You kind of get that for free, right? Also, this kind of philosophy of sort of like being bulletproof applies to some of the things that the compiler gives you. So for example, stdmath. Our stdmath passes lib C++'s test suite. In contrast, like if you're compiling with NVCC and you do something like std::sign f0, it's going to say like, I don't know how, it's going to say this function signf doesn't exist. And if you say, well, I take off the f, it says there's no std sign that takes an int. And that's like not standards compliant. Clang just works, and it's awesome. Similarly, I'm working on patches that will make std complex just work properly on Clang. They sort of work right now with NVCC if you're very cautious about how you use them, but what I hear from people who've tried to use this is they get into situations where their code will work at O2 and will crash at O0 because at O0 the complex functions don't get inlined and then it doesn't work with NVCC. So we're not going to have that problem with Clang. So that's why you might be excited about it on the front end. On the back end, I think the things to be excited about being able to use LLVM to compile your GPU code is that you can take the code that's important to you and optimize it and see where the compiler is failing and then fix the compiler. So let me give you 2 examples of that. In the GPU CppC paper, this is from some Googlers. This is kind of the predecessor to CUDA support in Clang. In this paper, they talked about an optimization of replacing 64-bit integer divides with 32-bit divides. So what they did was they check if both of the operands to a 64-bit integer divide are fit inside of 32 bits, and if so, they do a 32-bit divide, and if not, they do a 64-bit divide. This was a huge optimization. I don't know why, I don't know what code was doing this, but this like won really big on some of their benchmarks. And it was like a 4-line patch to LLVM because the thing to do this already existed for Atom processors. And so it was literally like, take this pass for Atom processors and now run it on the GPU. And you get like your benchmarks run twice as fast. Okay. And like, are 64-bit divides interesting to you? I don't know, because I don't know what your code looks like, but they were interesting to us. And so like, I claim that you can apply this same principle to your code. So let me just give you another example. We worked with some people from AMD to implement this optimization called a load store vectorizer, but I think LSW might be a better name, load store widener. The GPUs have instructions that will load consecutive addresses into multiple registers at once. So like ARM has similar instructions. And so we added an optimization pass to LLVM that will very aggressively widen loads and stores where possible. And what was really cool about this is that I didn't have to do the work. Some guy from AMD did the work for me, and it just works for NVIDIA GPUs as well. And this was, again, like a 2x improvement on some of our benchmarks. So I think this is really the promise of being able to use LLVM for compiling GPUs. So like I said, all this stuff is open source. It's actually being developed in the open. It's not just like code drop, throw some code over the wall style open source. If you want to play around with it, you can Google CUDA Clang. And the first hit is, I think, a set of instructions that I wrote. If they don't work for you, maybe send me an email. Or even better, send me a patch. I'm here for the rest of the conference. Just one final note, like we've been talking, there are a bunch of talks at this conference about like accelerators and GPUs and heterogeneous programming, and like this is really hot right now. We're thinking a lot about it. But when you think about it as like members of the standards committee or as like thought leaders in C++, like I urge you to think about how you can make something that exposes the low-level interface of the hardware. Because as accelerators become more important, like the whole reason we have accelerators is to accelerate our programs to make them run faster. And I don't want us as C++ to like get into a situation where we have these awesome accelerators and we have a language that kind of does not follow C++'s zero cost principle. Yeah. So I think CUDA does follow that principle, and I've heard some presentations this week that I think also sort of follow that principle, and so I'm happy with that. So I think we have about 10 minutes left for questions. Thank you guys very much. Yes?
Does CUDA-Clang also have implementation for passing classes with virtual functions?
So the question is, does CUDA-Clang also have the limitation of not being able to pass classes with virtual functions to device code? And the answer is yes. It's sort of a hardware limitation. And the reason is that the PTX assembler needs to be able to statically analyze your control flow in order to figure out where to insert those instructions that say, reconverge here. And as soon as you have indirect branches, you can't do that. So as a result, the PTX assembly language doesn't even let us do indirect jumps. So virtual function calls are just straight out.
Do you lose some optimizations by not being able to tell how many registers you're going to generate in your code?
So the question is, do we lose some optimizations by not being able to tell how many registers we're going to use? The answer is yes, but also compared to what? So there are no compilers that compile directly to SAS. So how badly we get hurt by that is unclear to me. The one thing I'll say is that NVIDIA does ship precompiled SAS blobs to do certain linear algebra and deep learning stuff. And there are some of those that we've been able to beat with like our CUDA code, but there are others that we have not been able to touch. For example, their matrix multiply. And the assumption is that the SAS that they've given us is hand optimized, and we're never going to be able to touch that unless we have a SAS compiler. Yes.
So would you rather that NVIDIA released this PTX stuff open source? Would you rather that all of this is implemented in Clang and NVIDIA just releases some sort of ISA specification?
So I don't have to repeat your question because you said it on mic. I'm not sure what I would rather have. I'd have to think about it. Although my instinct is like, I would rather that like the current way that we do things, where we emit this sort of, we emit essentially an intermediate representation. We emit PTX. Like, I think that I would prefer to have full control inside of LLVM and Clang, as opposed to continuing to release this this intermediate language. And the reason is that like, it would be certainly better if I could see the source code of the PTX assembler, so I could have some understanding of what it's trying to do. But on the other hand, I still don't control what it's doing, right? I can just understand what it's doing. And so we've had situations where like, we make uninteresting changes to to the generated code, and it actually has big changes in the SAS that gets generated. For example, it causes the PTX assembler to choose to unroll a loop or choose not to unroll a loop. And at the moment, I have no idea why it's choosing to do that. But even if I did know why it was choosing to do that, because I could read the source code, like that's still a lot of work for me to do. So yeah, I think I would prefer for it all just kind of to be in the compiler. Cool.
You mentioned that you were working with someone from AMD.
Yeah.
So is this going to be part of their HSA compiler, or are these orthogonal projects?
I really don't know, but I can put you in touch with the person who does know.
Okay.
Yeah.
Thanks.
What does this compare to if you compare this to GCC? If you're running on like a Linux-based or Unix-based platform?
Do you mean GCC for like compiling for GPUs?
Yeah.
Okay, GCC doesn't compile for GPUs, so
Okay.
there's no comparison.
Hi, I have kind of a dumb question, perhaps. Among the hardware bits in a standard CPU are like task state management.
Mm-hmm.
Do we have that in? How does this work? You mentioned a couple of kernels. It got me thinking. What's a kernel, and does one process on your machine just kind of occupy this hardware, or is it part of task switching?
So yes, you can have multiple kernels running. So what is a kernel, first of all? A kernel is like matrix multiply. It's like a single unit of compute, and in the programming model, I didn't show you the host code to actually launch the kernels, but if you Google CUDA Clang, we have an example showing you the host code to launch it. You basically specify what we call a GPU stream, and then you launch kernels on that stream, and they run in series. So you can say matrix multiply, and then subtract 12 from all of my elements, and it will do one thing and then the other thing. And those two things are kernels. And then to your specific question about task switching, yes, you can run multiple kernels concurrently on the GPU just from different streams. And you can have multiple processes touching the GPU too. It's happy to do that. I don't really know the details. I haven't tried to do that, but it does work. Yes? Sorry, can you speak up a little? So the question is this orthogonal to OpenMP? Yes and no. The CUDA language is definitely orthogonal to OpenMP. As you can see, it's a lot more complicated than just pragmas, or it's a lot different than that, I should say. On the other hand, OpenMP, I think, has an NVPTX backend, a backend targeting the same intermediate programming language that we target. So a lot of the optimizations that we write for NVPTX should work just as well for OpenMP. So the question is the long-term view for this compiler to take some standard call like std accumulate, and then just do analysis to figure out how to run the std accumulate code on the device, and then just kind of make that work, or is it something different? I would say right now we're not planning to do that. Instead, we're kind of planning to let you write code in this low-level language and make it run fast. And then if somebody wants to implement std accumulate, and I just went to a talk yesterday about this, with CUDA, knock yourself out. And there are languages, or there are libraries out there right now that support this. We support Thrust, which is NVIDIA's language, or library, I should say, that does that. But kind of my feeling about it is that I'm not sure that the compiler can do a good job about that. So for example, given the naive host code loop for the function I showed, just adding up a list of integers, it's not clear to me how to get a compiler to output the code that I wrote down.
So before PGI got bought by NVIDIA, they had a product, I think it still exists, where you can get CUDA to x86. So now that you have a full CUDA front end, has there ever been technical discussion about having a different back end to emit different SIMD vector instructions that aren't NVIDIA specific?
Yes, we've talked about that. I don't think we've had a ton of movement on that. And that's just because that's not something that our customers are coming to us asking for. But especially with AVX 512, before that, even with AVX 2, it's sort of dicey to do that in an efficient way. But with AVX 512, I think it's sort of clear how to do that in an efficient way. We just haven't done it, but it should be totally possible.
I have a question. Perhaps this is something you have run across and you have some ideas on how to micro-benchmark it. So the context is basically what you said about the warp divergence problem when you have those branches and you have different warps executing different branches. And to my knowledge, currently NVIDIA graphic cards do some kind of dynamic predication when we have this mask selection and different threads from different warps can execute different compute blocks. And I know that the recent cards have some kind of smart prioritization of those threads in the warps, so it's not just necessarily going to be one after another. And my question is, how do you figure out what that is? Because it's not exactly documented, and maybe it is something you have run across when you are trying to optimize the code you generate. Do you have some methodology to benchmark those things, or reverse engineer them?
What you say is news to me. I've never actually heard of that. I was under the impression, at least for the cards that I looked at, that it always executed one side of the branch and then the other side of the branch, and that was okay, fixed.
We can talk offline, but basically the keywords to look at is the warp divergence problem and dynamic predication, and that should be the first several hits. But
okay, yeah, we should talk offline about that. You guys got anything else? Okay, well, thanks a lot for coming.